have 2,000 synthetic detectors and 1,200 underground water cylinder tanks. This is the muon detectors. And the scintillator detector and muon detector, the detector array, the area is about 1.3 square kilometer. And the center is the water cylinder detector. The size is about 8,000 square meter. Okay, and now LASO has set up the a multiple metric collaboration network. It has signed MOUs with at least 8 international detector collaboration. For example, neutrino experiment, anti-race, chemistry net, Becker GVD, also the Cherenkov telescope, Veritas Magic, and also the large size telescope of CTA. And also the space-bound experiment such as Rosetta Damper. And the LASO collaboration has 300 scientists from the three countries and 32 institutions. Okay, and the LASO site is located at the Sichuan Daocheng, China. And the altitude is about 4,400 meters. The full array is completely built and in operation in 2021 in July. And it's easy to reach to the LASO site because the Daocheng airport is really close to the LASO site. The distance between the airport and the LASO site is about 10 kilometers. Here you can see here is the water cylinder detector. Okay, and the outside is the scintillator and the muon detector array. Okay, here I picture show you the muon detector. Muon detector is buried under the ground. It is covered by the 2.5 thick soil. And this one is the scintillator detector. Yeah, you can here see the picture of scintillator detector. Yeah, and the spacing of the scintillator detector is about 15 meters, and the spacing of the muon detector is about 30 meters. Okay, and the muon detector played a really important role for the gamma ray and the Compton ray discrimination. Here I show you an example of Compton ray event. You can see here in this event, a large number of muon you can be see. The circle represents the muon. This is the Compton event measured by LASO. And this is the gamma ray event measured by LASO from the crab. The energy is about 1 PeV. You can see the muon, a few of muon compared to the Compton ray event at the same energy. So here I will introduce you the water cylinder detector array. And here I have 3 pools, and with the total units about 3,100 units. Each unit size is 5 meter by 5 meter with 4.4 meter. This is the water water depth. Yeah, and in each unit they have 2 PMT. For the first pool, we are using the 8-inch and plus the 1.5-inch PMT. And in these two pool, we are using the 20-inch plus the 3-inch the PMT. Here I show you the energy range measured for the first pool, and this is the energy range for the these two pool. Okay, here I'll show you like a picture of the interior of the water pool. This is the 20-inch PMT. This is the 3-inch PMT, and this is really big event measurement by the 3 pool of Trinco the pool. Yeah. And for the 18 Trinco telescope, this is the telescope array, and each telescope has 5 square meters per meter, and also the 32 by 32 cylindrical array, and the covered field of view 16 degree by 16 degree. The pixel size is about 0.5 degree by 0.5 degree. And now I will introduce you some highlight result of LASSO. During our contract period in 2000, from 2019 to 2020, we are using the half array about 3,000 days data. We discovered 12 ultra high energy gamma ray stars in our galaxy. These stars we found it is energy spectrum, and there are no clear cut of up to TV. Yeah. So this is the power. This source is a Powertron. Let's review the widespread extent of the Powertron particle accelerator in our galaxy, whose acceleration capability have surpassed the traditional understanding. And the highest the highest photon is up to 1.4 PeV. So we think the LASSO started a new era of the ultra high energy gamma ray astronomy. And in after 2 or 3 years later, and we published the first catalog of very high energy and ultra high energy gamma ray source catalog, and we found the native gamma ray source. And in this source, and they have the 43 ultra high energy gamma ray source. And it means we from the 12 increased to the 23. Yeah, for the ultra high energy gamma ray source. Yeah. And the lost source is associated with the supernova resonance, the pulse wind nebula, and also the massive cluster, and also the and also the massive star cluster, and so on. So this provides a crucial set of best candidate celestial bodies for uncovering the origin of the high energy cosmic rays. And it is really interesting. 65 sources were found to be also associated with the pulse wind nebula, indicating that the PWN is the most efficient ultra high energy radiator. Okay. And we also measurement the energy spectrum from the Crab from Crab, and covering the 3-point decade of the energy, and the highest photon energy up to 1.1 PeV. And now, in fact, we measurement the collaborative energy up to 2 PeV. We not published now, not published in this paper. And clear, as you know, the pulse collaborator is the electron electron accelerator. So if we can produce the 1 PeV photon, we need 2.3 PeV electron. That means require 16% acceleration rate. This is really challenged our fundamental laws of electron acceleration. This that, but this also can not. This also can be. It also can be indicated later. This may be caused by cosmic ray. We mean the hydronics produce process. If the photon is produced by the electron, I think this is a strange of our knowledge of the electron acceleration model. Okay, water. And from those candidate source, the last is the first time we identify the cosmic loss candidate. This is from the thickness bubble. We in this bubble, the highest energy is about 2.5 PeV. This implies the presence of upper supernova accelerating photon to at least the 10 can be accelerated the cosmic rate at least 10 PeV. And here I show you the 8 gamma ray events above 1 PeV. Show you here the gray dot. Yeah, this is the 8 event. At event gamma ray event, and the highest I said before is the 2.5 PeV, and this is the 1.4 PeV is published in the Nature 2021, and to this 2 point is associated is this is the thickness OB2, and this is the thickness X3. Yeah. And the PeV photons are scattered in the bubble, and the things not to also with any small scale source. Yeah, this is the and the this is the extension really large for all the gamma ray events, and about 10 the bubble is the radius is about 10 degrees. Yeah, really large. And here I these the two components, the two patterns show you the associated. We found that our gamma ray is correlated with the gas distribution. This means the photon is produced by the hydronic nucleus, yeah, around the bubble, yeah. And yeah, actually I show you the signals elongated along the disk is. And it is tended to the 10 degree. Yeah. And we also test to show you this is not from the diffuse gamma ray. This is from the this gamma ray, most from the source. Here, yeah, I show you the two estimation. This means we are using the background gamma ray and the gas. We know they can produce how much the diffuse gamma ray. This two is estimation using the estimated one is the inner gamma ray, diffuse gamma ray, and this is the outside galaxy the gamma ray. I will introduce you later what is in the galaxy and outer galaxy. And this is our data. You can see the number of events exist the diffuse gamma ray at least 2 or 3 times. So we can get the conclusion that this gamma rays is from the source, not from the diffuse gamma ray. So this is the first time we identify the hadronic the gamma rays from the produced by the cosmic ray source. And also very lucky, and on October 9, 2020, NASA observed the brightest gamma ray burst, GRB 221009A. This is the brightest of all time. Also, this is the first gamma ray achieved by the ES detector. And why this this gamma ray GRB is so bright? This also found it is the open angle is narrow, is about 0.8 degree. It's really lucky to point to the laser detector, so we can see it. So that means it is really bright, so brightest. And this the trench is really rare, and it is once 1,000 or maybe 10,000 year event. Yeah. And we in 2007 seconds we measurement about 64,000 photons. This is compared to the Crab signals. We found it's almost the same as the exposure of the Crab for 400 days. This is really brightest gamma ray source. Yeah. And this gamma ray burst, GRB, the highest energy we have as a measurement is about 30 TeV. Yeah, above. This is this is really this is the highest photon ever observed until now. And this photon spectrum can be fit. This is the best fit is by the power law plus cutoff. Yeah, and also we have measurement the diffuse gamma ray. I said here is show you the inner gamma diffuse galactic plane gamma ray. This is the outer galactic gamma ray. And I said before, we estimated the diffuse gamma ray by using this in the diffuse gamma ray, the outer gamma ray, but we didn't measurement the thickness region diffuse gamma ray, but we know the gas of the thickness region, so that we know the gas distribution of these two regions. So we compare the different gas distribution, and we normalize the here the gamma ray diffuse gamma ray distribution to the signal region. So we know the signal region the gamma ray distribution. This is how we estimate the signal region gamma ray, diffuse gamma ray. And from this diffuse gamma ray in the galactic plane, we found the fluxes are higher than by a factor of 2 to 3 than predictions. This might be the one reason is maybe this they have some unknown source not be it's produced maybe we don't take out this unfound source, or maybe the propagation effect. The diffusion of the emission of longitudinal of the galactic plane was both visually high significance. And this is also the firstly detected in the outer galaxy region. And the supply index of both inner and outer region are about -3. And deviation from a single power law is not evident by the current data. Yeah. And also we can using the most anesthetic gamma ray above the bilateral to test the Lorentz invariant. And we now these are our first result. We published in the PILO, and we test the Lorentz symmetry and with the breaking energy 10 to 50 higher than 10 to 5 higher than the Planck scale, and it's a dozen of times higher than the previous result. Yeah.
You have 3 minutes left. 3 minutes left.
Okay.
Yeah.
Okay. Also, okay. That's and now and also here second order is still possible with the breaking energy 10 to 3 below Planck scale here. And also it can be used to search in the dark matter. And we are using the 570 days of LASSO data. We don't found the dark matter, but we can get the constraint on the heavy dark matter. And also this is the left hand is 10 times higher than the other experimental limit. And also we also have the now have measured the 19 the overall galaxy, and also we can from the galaxy we also do some constraints on ultra heavy dark matter property from the overall galaxies. This is now is opposite of PILO. More details you can see from here. Yeah. Yeah, a lot of the constraint is higher than the other experiment. And now here I change to the cosmic ray introduce you the cosmic ray measurement of LASSO. And the first result of the particle energy spectrum competition measured by LASSO, and we measured from the 300 TeV to 232 PeV. And here you can is the around 3.7 PeV. You can see the it's correlation with the mean logarithm mass. Yeah, you can see here the mean logarithm is from heavy to light as the energy increasing, and this is here the trend changed from heavy to light. Yeah, this means maybe the latency is caused by the light component. And for LASSO, the uncertainty is very small. Yeah, than the other experiment. You can see this is the uncertainty, the shadow. And the way LASSO can get so accurate the measurement of the our particle and the spectrum because we are using the intellect detector and plus the muon. And if it's better if we can measurement that actually happened in the short maximum, and they are independent to the primary component. But although here the short maximum not at our observation level, but this cause a little uncertainty. But we now have cylindrical telescope. We have the cylindrical size. So the cylindrical size is not the sensitivity too much to the solar maximum position. Also, the muon is also the number of muon is also not really sensitive to the source maximum. If we using these two information, we can get better energy control function, which is independent of the primary compensatory component. And this is the energy measurement. And we also want to measure the single element. So for LASO, it's a hybrid detector. So we have 4 kind of detector, and we have many mass density parameter. For example, Helix parameter, and also the energy deposited of the second particle near the short core, and the number of the particles near the short core, and really important muon information. So we have this is the distance. Distance is is the Helix parameter, one of Helix parameter, and also this is the muon. Number of muon, this is the number of particles near the short core, and we put those mass density parameter into the TMVA. You're using the multivariate data analysis is the best. We can select a single, we can just proton. You get a very high